Good afternoon, good morning, good evening, good night, wherever you are in the world. Welcome you to the ISTA-ISSS webinar session today here, and we have two ladies here. The topic today is seed supply and storage with a focus on tropical tree species. And we will start with the presentations in a few seconds. First, let me give you a few information. If you want to ask questions, please put them in the question and answer box, and we try to answer them. If we don't have time enough to answer all questions, we will forward all the questions also to the panelists, and you get an answer for your questions. And I would like to welcome today Karen Somerville and Elisa Vera. Karen will start with the first presentation today, Tools for the Conservation of Rainforest Seeds. This will be followed by Elisa's presentation, Tropical Tree Seeds, Supply Testing and Solutions. Let me introduce you, Karen. For those who do not know, first of all, welcome in your very early morning, Karen. Karen is from Australia, so that is not a very convenient time for her. There may be some people from Australia here, or they want to look at it a little later, because as all our ISSS ISTA webinars, these webinars are recorded and will be made available at least on the ISTA YouTube channel for everybody to look at. So Karen is a research scientist at the Australian Plant Bank, a premier conservation and research facility within the Botanic Gardens of Sydney. With a background in horticulture, Karen has been dedicated to plant conservation research since 2003 and is an active member of the ISTA Seed Storage Committee. She currently leads the Rainforest Seed Conservation Project, which focuses on identifying Australian rainforest species suitable for seed banking, assessing their seed longevity, and advancing alternative storage methods, including tissue culture and cryopreservation techniques for species with challenging storage needs. Under Karen's guidance, her team has collected extensive germination and seed rate data for over 400 plant species across diverse families, contributing vital insights to rainforest plant conservation. From these studies, they have developed an accessible key to help assess storage behavior, especially valuable for seeds that are limited in availability or challenging to germination. Thank you for joining us, Karen, today. And I know you may also be in future a member of another ISTA committee, but that's something which is still secret among the two of us. I hand over now to you, and we are happy to follow your presentation.
Thank you, Andreas. Just open this up. All right, hello everyone, thank you for joining us. So as Andreas said, I'm from the Botanic Gardens of Sydney, and I just want to start the session with a chat about rainforest seeds. Not all of the species that I'll be talking about today are from tropical regions, and they're definitely not all trees, but we'll be including some tree species and tropical species as well. So just to begin with, a little bit of background. As Andreas said, I'm from the Botanic Gardens of Sydney, and that's made up of 3 botanic gardens on the east coast of Australia. You can see that little blacked out wedge there. That's the state of New South Wales, where we have a license to collect. So the original garden was on Sydney Harbour. That's this Royal Sydney Botanic Garden. And we have a garden in the Blue Mountains at Mount Tomah that grows cool climate plants, and I'm based at the Australian Botanic Garden at Mount Annan in the southwest. And that garden specialises in the display and conservation of Australian native species, and within the garden we have the Australian Plant Bank, which is a facility supporting in situ and ex situ conservation. The heart of the building is a seed vault where we store seed collections for around 5,000 species of New South Wales plants, and as well as other species from around Australia. We also have facilities for tissue culture and cryopreservation and associated nursery facilities for growing threatened species. One of the vegetation types we're particularly interested in conserving is rainforest species. And I know Australia is not generally associated with rainforest around the world. It's a particularly dry continent for most of the part. But 50 million years or so ago, the entire continent was covered with rainforest vegetation. And as the continent broke away from Gondwanaland and shifted its position, the continent dried out and the rainforest was pushed to the edges of the continent. So what we have now is sort of a fragmented rainforest that runs along the east coast and a little bit along the northern coast. And that includes vegetation that ranges from wet tropical rainforest, monsoon rainforest, down as it heads further south through subtropical, warm temperate and cool temperate rainforest types. And those rainforests hold quite a lot of diversity. Even though they only cover less than 0.5% of the continent, they hold more than 3,500 seed-bearing plant species and hundreds more ferns and mosses. So we have a really strong interest in conserving those species. And unfortunately, the rainforest diversity, of course, is under threat. We've had a lot of historic land clearing that has reduced the little rainforest that we did have even further. And as an example, there's an area in New South Wales known as the Big Scrub that was 75,000 hectares of continuous subtropical rainforest. And between 1860 and 1900, that was reduced to just 100 hectares of fragments. And species in those isolated remnants have a reduced genetic pool. They've got reduced opportunity for crossbreeding, and so they have an increased risk of inbreeding. And the edges of the fragments are more exposed, and so they're more prone to weed invasion, more prone to drying out, so they can be more prone to burning. And we also have some issues with disease. So in 2020, we had some major bushfires in Australia, and they actually burnt 55% of the Gondwana rainforests in New South Wales. And that was a huge amount of the rainforest vegetation. A lot of that is slowly recovering, but it does take a while, and it has a big impact on the seed availability. And the other major problem that we're facing at the moment is myrtle rust, which is a disease that arrived in Australia in 2010. And it spread rapidly up and down the coast. So it's all the way from the top of Australia now, all the way down to the bottom. And this disease affects more than 380 Australian native species in the Myrtaceae family. Repeated infection kills off the foliage. Before it gets to that stage, it also reduces seed production, and eventually the plants are killed. And we have a few species that have gone from being quite common in the rainforest to now being critically endangered as a result. So we're quite interested in finding solutions to use to preserve the diversity that we have left. And we started to think that maybe seed banking could be part of the solution. So we have quite a lot of experience in conserving species from dryland communities. Many of our Australian species can be successfully stored at 15% relative humidity and minus 20 degrees under the standard seed banking conditions. And so we wondered if rainforest seeds could possibly be conserved in the same way. But we had the expectation that based on a study by Tweddle and his colleagues in 2003, we had the expectation that at least half of the woody species would be sensitive to desiccation and not able to be stored. So the Rainforest Seed Conservation Project was initiated to assess the response to drying under standard conditions and storage at minus 20 degrees Celsius. And then we wanted to look at comparative longevity in storage and plant and environment traits that were associated with the storage response. This work was first started by Kim Hamilton around 2009, and she published in 2013, I think it was about 68 species. Initially, she was just looking at desiccation sensitivity. So then we've expanded it since then to look more at the storage possibilities. There was a study by Sarah Wise and John Dickey that was released in 2017 that found that the storage behaviour of species within a genus could be a good predictor for other species in that genus. So we had a look at shared genera across the South Pacific and which ones we had information for, and we found that there are more than 790 genera that we didn't have any information on storage behaviour for at all. So hopefully the results that we're going to talk about today will be applicable across the South Pacific and also to some genera in Southeast Asia. So the core research for the project involved seed collected from the east coast of New South Wales. So that was mainly from subtropical to cool temperate habitats, but a number of the subtropical species had distributions that extend to tropical rainforest further north. So we sampled a variety of different plant habits, from herbs through shrubs, vines and trees, and a variety of different fruit types. And the basic research involves just collecting the seed, germinating it when it's fresh, germinating it after drying at 15% relative humidity, and after drying and storage at minus 20 degrees. And that sounds like such a simple plan until you discover that rainforest seeds can be quite difficult to collect in good quantities. They're really prone to contamination, fungal contamination, and quite a lot of them have dormancy, which was something that we weren't expecting when we started the project. If you're interested in looking at the germination conditions, this odd-looking link here will take you to a supplementary file that has conditions for 162 species that we're presenting today. So we also collected some environmental and trait data to go along with the seed storage behaviour data. We looked at the distribution, whether the species occurred in wet rainforest only or in dry rainforest only or in both. We looked at environmental traits like latitude, rainfall, average, max and annual temperatures, the plant habit, the fruit type, whether it was fleshy or dry, dehiscent or indehiscent, fresh seed moisture content, the oven dry seed weight, seed coat ratio, which is the dry mass of embryo to the dry mass of the whole seed, and a value known as the potential, representing the potential for desiccation sensitivity, and I've just noted it here as PDS, and that combines the dry weight and the seed coat ratio in a formula developed by Dawes and his colleagues in 2006. So we've looked at around 400 species so far, and because we've had issues with poor seed quantities and dormancy, what we have is 162 species that we've published so far that we were able to get germination greater than 50% for. For those 162 species represent 63 families in rainforest. And what we found so far is that only 22% of the species were sensitive to drying, which was a really good outcome for us. 64% were fully tolerant and 10% were partially tolerant, meaning that they showed a significant reduction in germination after they'd been dried at 15% relative humidity, but they were still germinating fairly well. And so that indicates that maybe if we adjust the moisture content, they'll be storable. So all in all, that was 3/4 of the species that we've tested so far that are potentially bankable, which was a really great outcome. So I don't expect anybody to read this slide, but I just wanted to give you an idea of the range of genera that we had a look at. So there's 133 different genera listed here. For about 18 of those, we were able to look at 2 or more species within that genus. And in 14 of those genera, the behaviour was consistent among species in a genus. And tree species, as we were expecting, had significantly more desiccation-sensitive seeds than any of the other habitats. So that agreed with Tweddle's work, with the exception that we found relatively low levels of desiccation sensitivity in the shrubs and plants that flower as both a shrub and a tree. The response to drying was also related to the seed traits that we measured. So sensitive seeds had significantly higher fresh seed moisture content than seeds that were partially or fully tolerant. And they had significantly higher dry weight. For the seed coat ratio, the sensitive seeds had a significantly lower seed coat ratio than the seeds that were tolerant or partially tolerant, and a significantly higher p-value, which was the value developed by Dawes for combining the seed coat ratio and dry weight. I just wanted to point out here that for that p-value, there's quite a big range in the values that we found for the different species that were sensitive. So we'll come back to that later. So for all of the data that we collated, we decided to combine it into ordinal logistic regression and see what came out as significant predictors. So for the first model, we used 156 of the species, and we included habitat distribution category, the plant habit, latitude, rainfall, mean, max and annual temperatures, the fruit type, whether it was fleshy or dry, and the seed dry weight. So for this first model, we had to leave out the data on seed moisture content and the PDS value because we weren't able to get that data for all of the species. So we ran the model with all the predictors initially, and then we removed them one by one, taking out the least significant predictor at each time until we were left with only the significant ones. And what we ended up with was that plant habit and fruit type were the only significant predictors of desiccation sensitivity, which was really interesting. The trees were 5.3 times more likely to have desiccation seeds than plants with other habits, and fleshy fruits were 4.8 times more likely to have desiccation sensitive seeds than the dry fruits. Keep in mind that the 5.3 times more likely includes many trees that also had desiccation tolerant seeds, and in terms of the fleshy fruit, there were many fruits that also had desiccation tolerant seeds. So it's not the best predictor, but it was an interesting result. So then we did a subset of those species that we had moisture content and data on potential for desiccation sensitivity. And we modeled those, including the significant variables from the first model. So this model excluded species with the very small seeds that we didn't have any of that data for. And in this case, it was fresh seed moisture content and the calculated potential for desiccation sensitivity that were the only significant predictors. And so increasing seed moisture content and that increasing value for potential for desiccation sensitivity meant that there was an increased probability of desiccation sensitivity. So again, that's all very interesting, but it wasn't necessarily giving us indicators that we could use on a reliable basis for assessing desiccation sensitivity. So we combined our data with data from the initial study done by Kim Hamilton and studies done by Lan et al. In China in 2014, and the study by Dawes and his colleagues from Panama. And we just divided all the data into categories that had roughly equal numbers of species, and then had a look at the spread. And what we found was that the seed traits were most useful as predictors of drying response within a certain range. So for dry weight, seeds that were 20 milligrams or less were almost always desiccation tolerant. And then above that, you've got an gradually increasing proportion of desiccation sensitivity. Likewise for the fresh seed moisture content, so seeds with a fresh seed moisture content of 20% or less were always desiccation tolerant. And then above that value, then you had gradually increasing amounts of desiccation sensitive species. And then we had something similar for the calculated potential for desiccation sensitivity. So values that were less than 0.01, always tolerant. And then this value to the far right was the one that Dawes was recommending as a good indicator for desiccation sensitivity. And his study found that 85% of species with a PDS value greater than 0.5 were likely to be desiccation sensitive, and that agreed with that combined data that we have here. So one last thing I'd like to show you here is some qualitative data on seed morphology, which can also give an indication of drying response. And on the left, we have the species that were sensitive to drying, and on the right, a sample of species that were tolerant of drying. This probably would have been easier to look at if I'd made the seed sizes relative, but the scale bar represents 2 millimetres in each case. And so the seeds on the left are at least 1 centimetre in length, and the ones on the right are less than half a centimetre. So seed size, so very large seeds and with a developed embryo and often with no endosperm, and in some quite often green, these seeds were sensitive to drying. The ones that were tolerant of drying tended to be smaller. They were more inclined to have endosperm, and they were less likely to have a green embryo. So nothing definitive that you could use to definitely say a seed was definitely desiccation sensitive or desiccation tolerant, but it's an interesting thing to throw into the mix. So because we had this situation where we've got the values of traits at the extreme edges of the possible range that are useful, but the ones in the middle are not so useful, we decided to skip modelling, and we thought we'd try developing a key instead. And so what we came up with was this simple key to assess the response to drying. And it just starts with looking for information on storage behaviour in the genus. So I'm sure you're all familiar with Q's seed information database, and that is now available again. And if you just search that and find if there's any information on the genus, and if the information is that the species are consistently orthodox, then the species that you're looking at that hasn't been tested before is quite likely going to be desiccation tolerant. If the behaviour is consistently recalcitrant, then likewise you're likely to get a desiccation sensitive seed in the one that you haven't studied. But if the seed storage behaviour in the genus is inconsistent or there's no species tested, then you go to the next step and you look at the seed coat and just dissect it to see if you've got a hard seed coat. And we know from Tweddle's study that seeds that have physical dormancy, that have that hard seed coat, are desiccation tolerant because they have to dry out as a process of developing that physical seed dormancy. So you can check the seed coat, you can do a test to see if the seed will imbibe to confirm whether or not it's permeable or impermeable. And then if that doesn't give you any information on the desiccation sensitivity, then you can go to the next step, which is just looking at oven dry weight and so on. So look at oven dry weight, then you can go and look at the calculated potential for desiccation sensitivity, and then finally you can have a look at some seed morphology. So this worked quite well for our data set. I'm sure we'll refine it in future when we have more information, but for the moment this placed more than 90% of the species that we looked at into the right category when we ran them through this as a test. So we're still going with the testing for the storage behaviour, and I've got another 60 odd species that I'm working on at the moment that are drawn from cloud forest in tropical Queensland. So we're still working with that. We're still working with putting species through this key and seeing how the actual results compare to the key results. So that will be published a little bit further down the track. But in the meantime, what I want to talk to you about next is the storage behaviour, which was very, very interesting. And we found that quite a lot of the species that were desiccation tolerant ended up being quite sensitive to freezing. So this is just a sample of some of the species that we've had a look at. And it's the bar on the left that is brown is showing you how they responded post-drying, and then in the blue on the right we have the response post-freezing. And within a few years, a lot of the species that we looked at there were showing big reductions in germination potential. And under accelerated aging, we found that rainforest seeds were quite short-lived compared to species from other habitats. So in here, we were aging seeds at 60% relative humidity and 45 degrees Celsius. and estimating the time for germination to decline to 50% using probit analysis. And we compared the results for 36 species to 52 species from other habitats, all collected from the eastern edge of New South Wales. And the rainforest restricted species were significantly shorter lived. So we've got this issue now where we go to these great efforts to collect rainforest seeds, which isn't necessarily always easy. They've got to travel quite long distances, we've got to battle the leeches and the snakes and all the other sorts of things you get in the Australian bush, and battle the problems with poor seed quantities. And then when you get them back and then you find that they're desiccation tolerant, you get all excited and put them in the freezer and discover that they're not going to last very long in storage. It seems like quite a big waste of effort. So we started a project that was funded by the Ian Potter Foundation using thermal analysis to look at what might be happening during freezing and thawing that might be causing the short-lived nature of these species. So this, if you're not familiar with it, just involves putting a seed sample into an aluminium pan. We lower the sample temperature down to minus 150 degrees, raise it back up to 50 degrees, and we use a rate of cooling and warming of 10 degrees Celsius per minute. And then any changes in energy that are occurring during freezing and thawing are recorded and plotted on a chart that we can look at and analyse afterwards. So this is an example of the output. This is for Rhodamia maydeniana, which is a rainforest tree that we know is short-lived in storage at minus 20 degrees. The bottom line shows what's happening to the seed as it's cooling, which appears to be not very much at this rate of cooling. And the top line shows what's happening as the seed is warming. This is our normal storage temperature at minus 20 degrees, and you can see that there's a major energy transition occurring at minus 20 degrees at the temperature that we're normally storing. This is Syncarpia glomulifera, is in the same family. It's also a rainforest tree that grows in wet sclerophyll forest. And this one has survived quite well for 15 years in storage at minus 20 degrees. And just by contrast, for the warming curve, this is again is our storage temperature. And for this species, there's nothing much happening at minus 20 degrees. So what we were hoping was that the thermal profiles for these species would show us what was going on around minus 20 degrees and also whether there were alternative temperatures that we could use for storing them. So this is the results for two of the species. This is on the left, Archaeodomertus beckleri, and Rhodamia maydeniana again on the right. And this is the warming profile that we're showing here. The red line shows the storage temperature of minus 20. Blue patch on the left shows that there's nothing much happening at temperatures below minus 100 degrees. And then there's also no transitions happening between about minus 10 and 4 degrees. So those look like possible alternative storage temperatures that we could use. The reactions that you can see are attributable to the crystallization and melting of seed lipids. And when we extracted the lipids, they showed very similar sort of profile. So these results suggested that storage outside the range of thermal transitions might be more suitable. And so we set up some experiments testing a range of different temperatures to see how the seeds survived. And this is for Rhodamia maydeniana, which was stored for 12 months at 15% relative humidity. Here's what happens when we store it at minus 20 degrees. And so it had significantly better survival at 4 or minus 5 degrees Celsius. We found the same for Archaeodomertus beckleri. Here we tested seeds dried to 15 and 50% relative humidity. Oh, the 1 a.m. time slot's getting to me. And again, they still did very poorly at minus 20 degrees, and they had significantly better survival at 4 or minus 5 degrees. We saw the same pattern for one of the macadamia species, Macadamia jansenii and Macadamia integrifolia cultivar, and for several other species that we've tested so far. So we have two useful tools we're now using to aid the conservation of our rainforest species. The first is a simple key to assess the response to drying, And then we have thermal analysis to identify the species that are potentially short-lived at -20 degrees and identify alternative storage temperatures. And that really reduces the amount of time that we have to spend finding out that the seeds are desiccation or freezing sensitive. And those two tools will hopefully increase the speed of assessing which species can or can't be conserved by seed banking, which will really give us a help in our mission to save the species that are left. Guys, before I finish, I just want to say a big thank you to past and present team members of the Rainforest Project and to our funding bodies who we have quite a range of different organisations and people who support the project, and we're very grateful for their support. Well, that's it from me. Thank you.
Thank you very much, Karen. That was very interesting. I start to get questions in. We do that after we heard Elisa's presentation. And I would like to take the opportunity to introduce Elisa to the audience as well. I've only got one question here. Do you want to answer it now?
Yeah, sure.
Okay. Have you looked if there is an association between seed coat, seed size ratio, and dehydration tolerance inside some species?
So I'm not sure what that question is. So the seed coat ratio, yeah, there was definitely a relationship
Seed
to
coat, seed size ratio, maybe both in that case.
this. Okay. So yeah, well the seed coat ratio looks at the ratio of the weight of the embryo to the weight of the whole seed. I'm not sure if that's what the person meant. And yeah, and it is definitely an indicator of desiccation sensitivity or desiccation tolerance, but not a clear one.
Okay. I have no more questions.
Okay.
And just to remind everybody, if you have questions, please put them in the question box, and then we continue with the presentation of Elisa. Elisa holds a degree in agronomy from Federal University of Lavras, where she also completed her master's and the PhD in agronomy with a specialization in phytotechnics, focusing on seed production and technology. From 2004 to 11, she served as a researcher at the Biotechnology Center of CUDEC, the Central Research Corporation, working with molecular markers on breeding, tissue culture, and transformation of large crop plants. Between 2009 and 11, Elisa was a professor in a postgraduate program in biotechnology applied to agriculture at Universidad Paranense, Unipar, where she guided research in the use of molecular markers. Currently, she is a researcher at Embrapa Forests. She works as a technical manager of the Forest Seed Laboratory Centers on germination seed storage and the selection of seed collection matrices, all informed by genetic studies and statistical methods applied to forest seed technology. She also serves as a co-advisor for postgraduate students in plant production and forest engineering at the Federal University of Paraná, contributing her expertise in forest seed and technology. And in addition, Elisa is an active ISTA member and currently serves as the chair of the ISTA Forest, Tree and Shrub Committee. Thank you, Elisa. The stage is yours now.
Okay, good morning, everyone. First of all, I would like to thank you, Andreas, for the invitation to do this presentation, and thank you the people who are attending this meeting. I will share my screen. Okay, so the title of this presentation is Tropical Tree Seeds, Supply, Testing, and Solutions. Andreas already introduced me, and in this presentation, I will talk a bit about these topics. Tropical forestries, a bit about the area, biodiversity and importance, tropical trees.
Sorry, Lisa, it looks like you are not, we cannot hear you. And you
Yeah,
cannot
we
hear.
can
Now
hear.
your voice is coming back.
Uh, it's
And we are
better
not
now.
seeing your presentation.
Oh, let's
Now your
start.
presentation. Thank you
Let's
very much.
start again. Mm, shall I start again
Yes,
or
start
okay?
again. We
Okay.
didn't see in the first place, but we got lost.
Mm-hmm.
Maybe there's a connection problem with your
Mm-hmm. Is it
earphones.
okay now?
Very good. Thank you very much, Elisa.
Thank you, Andreas. So, starting again, this presentation, the title is Tropical Tree Seeds, Supply, Testing, and Solutions. Andreas already introduced me, so let's start. In this presentation, I am planning to talk a bit about tropical forests, area, biodiversity, and importance, tropical tree seed supply and solutions, and also testing and solutions. Just to remind you, the tropical region of our planet is between in tropical Cancer and Tropic of Capricorn. In this area, we can find the most part of Latin America and Africa, and a small part of Eurasia and Oceania. And in this tropical region, we find the tropical forests. In 2022, this article, The Number of Tree Species on Earth, was published, and the authors analyzed the two big database of tree species available, the GFBI and the Tree Change, and they concluded by doing estimations that there are 73,274 tree species on Earth. In this map, in this figure, in this photo that you can see on the slide, only South America and Africa, they respond for more than 50% of the tree species on Earth. The exactly number, uh, the putting together the number of trees of South America and Africa, we have 42,000, almost 43,000 of tree species only in these two regions of the tropics. So the tropical forests respond for the largest forest cover of the planet. And this type of forest, they are responsible for climate regulation, water supply, and carbon stocks on the planet. In the recent years, the researchers have shown that the carbon stock is not only on the leaves of the trees, but also on the roots. The most part of soil carbon stock is made by the roots of the trees. We are in a time of the United Union decade on ecosystems restoration. Until 2030, it is supposed or intended to restore 350 million of hectares. For these reasons and to trying to attend this restoration, several countries and continents are doing efforts to reforestation and recover some forest areas. For instance, Brazil, we have the task of 2 million hectares recovered. In Africa, the whole continent is intended to reforest 100 million hectares. But for to attend to have enough seedlings and seeds to restore these areas, we have to ask if we have a quantity of seeds for this. Just an example, in Brazil, we are producing 2,600 tons of native seeds. This production, it's better. Nowadays, Brazil produces 70 tons of native seeds per year. To recover the 2 million hectares of forests, we had to produce 2,600 tons of native seeds per year. So you can see a big difference in the reality and between the reality and the intention. And this number, 70 tons, it's considered a good production. It's important to say that in the restoration scenario, we are talking about more about native species. To attend these restoration programs and to have enough amount of seeds, we have to talk about the tree seed supply. A good initiative has been the work together with local communities, like indigenous and people who live near the forests. The organization of these local communities is called seed networks. In Brazil, in the beginning of 2000 years, a lot of seed networks was created. And from that time until now, some of them already exist and they are very well organized. And examples are the Xingu Seed Network, the Cerrado Seed Network, and the Vale do Ribeira and the Arboretum Program are seed networks for the Atlantic Forest. Just to mention, in Australia, as we had Karen here from Australia, there is some initiatives of seed networks, and one of them is the Geoghannian seed operation. It's a producer of seeds to attend the mine site restoration. In this slide, you can see some actions that are being realized in Brazil with the local communities. This in the photo, in the image A, you can see a community workshop held in the Vale do Ribeira seed network. And in B, you can see native seed grass collection in the neotropical savanna of central west region of Brazil. In letter C, in the image C, installation of an indigenous owned and operated native seeds farm in Morawa, Western Australia. And D, the Iarangi women movement processing native seeds in the Xingu indigenous territory in the Brazilian Amazon. These local communities, the people of these groups, they must be prepared as collectors of seeds to attend the seed network. For this reason, a lot of capacity building has been worked with these groups. We have to train them in basic knowledge, for instance, to identify the right harvest point. We know that for native species, it's very important to collect the seeds in the right moment. And the window of this right point is not so large. Here in this slide, you can see a graphic as an example of the definition of the right harvest point for one native species in Brazil. It's the species, the Vernonantura discolor, and this was a research work made here in Embrapa Forest, and we could define the right point, observing the dry matter, the germination, and the vigor of the seeds. We have to try to teach the local communities in the recognition of this type of issues. And for this, we have been working with some online course development, for instance, for the indigenous population. This course, the name is Sowing Forests in the Indigenous Lands. This online course was developed for 11 native species, and in a very simple language, we tried to show for the indigenous how to recognize the right time of harvest, how to process the seeds, how to do the germination, and how to storage the seeds. You can find this course in this website. Unfortunately, it's in Portuguese, but you can add the legends in other languages. There are three approaches for native seed supply. We can collect the seeds in natural populations, in managed population, and in the called cultivated areas. Comparing these three approaches, in natural populations, we have the best genetic representation of the population. And we have a high damage, you have chance to damage the trees, and the productivity is very low. The managed population, from this point to cultivated production, we can reduce the damage of the trees and obtain high productivity. This cultivated production can be done in the seed orchards, outdoor or indoor. In Brazil, we have a good initiative to build indoor native seed orchards. This could be a solution, but it's also a big challenge how to cultivate these native trees indoor. But on the other hand, we have guarantees to maintain the genetic quality. Once in the seed supply, it's very important for restoration and reforestation. It's very important to keep in mind the genetic quality and not only the physiological quality. Here you can see a native seed orchard outdoor here in Embrapa Forests. It's a very old plantation of Araucaria angustifolia. The age of these trees is 40 years old, and in this orchard we have represented, we have 12 provenance represented in this orchard. This orchard is in the south area of Brazil, in the Paraná state. In this slide, you can see a commercial seed supply arrangement, a very organized supply arrangement. You see the seed producers in the beginning and the producing seeds to seed users. And between these two stakeholders, we must find the seed testing facility. The seed testing is come to three seeds to answer several questions. I just added one here from NOBS, one of the NOBS questions. Does the sold seed have the potential to produce a healthy plant? This is a very important characteristics, one of them, to sell the forest seeds. Regarding this tree seed testing, we have several challenges. We have few methodologies for native seed testing, and a lot of work has to be made for this development, but we can find the methods published in good journals, and this can be found. The method validation is a complex procedure according to the rules, and how they are preconized today, it's not applied for native forest seeds. We need to do some corrections or some improvements in these procedures to fit better for the case of native species. And the ISTA is working on it. We have a work together with the Statistics Committee, trying to simplify and to adapt the validation procedures to the reality of native forest seeds. And another challenge is the test's duration. We need fast tests development. For instance, the tetrazolium test is a very good test recommended for tree seeds, but we don't have a lot of methodologies developed. In this slide, you can see an example of the peach palm. This is the common name of Bactris gazipais. It's a native species in Brazil. It's a recalcitrant species. The vigor, the duration of the vigor is not more than 60 days, but the germination test, according to the rules, it takes 120 days. In other words, when we have the result of the germination, the vigor, the seeds are not vigorous anymore. We developed a tetrazolium test methodology to solve this problem. And this tetrazolium test is very, very simple, and it takes only 2 days compared with the more than 100 days for the germination test. You can see here on the photos the viable seeds and the non-viable seeds. We evaluate also the embryo and the endosperm. Here you can see with these peach palm seeds, doing a relation with the cutting presentation, you can see the type of the seeds that is recalcitrant seeds, big seeds, and with a thin coat. Currently in Brazil, we have the Brazilian rules for seed testing, and we are working in the next edition. The Agriculture Ministry is working in this next edition that is planned to be published next year. The new part of this next edition will be a chapter dedicated to forest species. It's a very new position of the Agriculture Ministry, and I believe it is due because it's due. It can be explained because the demand of forest seeds, native forest seeds in Brazil is high. In this new edition, almost 250 forest species are included. But in this list, that is a large list, we don't have yet 66 native species that has economic importance for the seed networks. For these species, we don't have germination, neither TZ methodologies, but we can find them in published literature, and the Agriculture Ministry is already considering to include these methodologies in the new rules. So, as a last message, I'd like to say that it's very important to work with the local communities to attend the tree seed supply. This group of people are very important to have to attend the necessity of high amount of tree seeds. And we have to consider the development of seed tests for the new species. Thank you.
Thank you, Elisa, for that very comprehensive presentation. I am looking at the question and answers box, but I don't see any questions, except the one which was answered by Karen before. You get a few of clapping hands here, so I assume there are no big questions. We talked today about tree seeds mainly, but we also know that similar questions need to be answered for other wild species, not only trees, not only tropical areas. And this will be in future a task for the Wild Species Committee at ISTA. Just want to mention that, which was a working group before, and it was transformed a few months ago at the annual meeting by the executive committee into a committee that has a little bit more possibilities to work, and we hope that we can take up a number of wild species and hopefully also tree species with the information you distributed and Karen mentioned that people can participate and get information from this committee, which will probably be in form of a website. Um, Let me have a quick look. Karen is still there as well. If you could join us here for a minute. Yeah, I know it takes always a little while until the camera goes on. Yeah, your presentations must have been pretty clear, but if anybody has got questions afterwards when they look at this webinar again or flip through the presentations, you are still available to answer questions probably. I'm very sorry that I don't have more questions here, but it looks
Andreas,
like
I can actually see some questions.
I don't see anything in the question and answer box.
Ah, it's in the maybe it's in the chat. There's a question here from Stephen
Oh,
Groot, but I can't read the whole
oh
thing.
yeah.
It's
Now things came up. Uh, yeah. Did you test the effect of warming at -20 sensitive seeds to, for instance, 35 degrees before testing germination? We had experience with loofah seeds that could be brought to germination by short warming.
mm, yeah. We did try that during. Did you mean during thawing, Stephen? We tried compared warming it in a water bath at 40 degrees to warming at room temperature, and it had no impact. There was no impact to the response to the storage temperature.
Um, Let me see. Are you planning to do research on including desiccation tolerance in recalcitrant seeds? Who wants to
What,
answer that one? What, that was the answer, right?
what was the question?
Are you planning to do research on including desiccation tolerance in recalcitrant seeds?
That's my life.
That means a clear yes. Uh, yeah, here's another one. Seed coat seed size ratio is a prediction of desiccation tolerance sensitivity among species. I wonder if different seed sizes in the same species would lead to a different dehydration tolerance.
Ah, I see. Okay. Oh, that's an interesting question. Um, it would be very interesting to look at, especially in some of the bigger species. We have noticed that definitely there's a difference in the rate of drying between different sizes in the same species. For example, for in the macadamias. Um, but yeah, it would be interesting to sort of separate out the smaller seeds from the larger ones and see how they both respond to the desiccation.
Okay, then oh, things are coming up now. Try to get something from here. Can you speculate if we were able to physically restrict the growth of a desiccation-sensitive seed on the plant, would it improve its desiccation dehydration tolerance? That is more
Hmm,
physiology, probably.
interesting question.
Yes, the question is, does the seed learn something which the plant is helpful to the plant?
Hmm,
Huh.
I don't have an answer for that one. Although it would be interesting to see whether seeds produced under stress might be more desiccation tolerant. So under slightly drought conditions, maybe they would have more desiccation tolerance. That sounds like a big project.
Maybe that is for Elisa. What is the percentage of rainforest species, if any, that produces desiccation intolerance recalcitrant seeds?
What's the percentage?
The percentage of rainforest species, if any, that produces desiccation intolerance recalcitrant seeds.
The percentage between these two groups?
Probably, yes.
Yeah. We don't have the most part of the rainforest species, at least I can say in Brazil, we have a lot of tolerant species. Mainly in the Amazon, we have the recalcitrant species. In the humid areas, we have more recalcitrant species. Maybe in Australia is like this also.
Hmm. Yeah.
Maybe another question for you. Oh, you want to say something, Karen?
No, no, that's okay.
Okay. Maybe another question for you, Elisa. At what stage are seeds collected? Physiological stage or controlled period after observing ripening?
In the training of the local population, they say.
Yes.
We are trying we present all this information. And these local populations, they are building storage rooms to keep the seeds. I don't know if I'm answering the question.
I think so.
Yeah. And we are trying to in this capacity building, we are trying to explain and teach all this physiological knowledge in a very simple language for these people understand how to deal with better with disease.
Thank you. Um, Maybe to both of you, the last question I see here. Did handle the issue of dormancy when assessing the sensitivity to desiccation?
Sorry, could you say that again,
Dormancy.
Andres?
How did handle the issue of dormancy when assessing the sensitivity to desiccation? I think it has to do with dormancy and desiccation.
Yeah, yeah. Yeah, it's a tricky issue if you're using the standard methods for assessing seed storage behaviour. If you can't germinate them, then how do you know what the response is? But I think Eliza was mentioning doing tetrazolium staining, and that might be one solution. Difficulty of that with wild species is that you don't always have the luxury of developing the standards and knowing exactly what you're looking at as far as the stain goes and what's viable and what's not. But yeah, that is one option.
Yeah, I agree. The only solution is tetrazolium test.
Mm.
And I think people think that its tetrazolium development methodology is difficult, but it's not a rule for the species. For Bactris gazipa, is the peach palm that we developed here in Embrapa Forest, it was very, very easy. Very easy.
I got a lot of congratulations here as well to all of you. And the question of some missing of the presentation and slides. The recording will be available on the ISTA YouTube channel, and I think we also make available the presentations from your side. And there's a big thank you as well from Julia Whitting, the president of ISSS. Julia, if you want to say a few words, we could let you in as well. I can see if I can do that. Um, like, Julia, you may be able to join us now if you want to say a few words.
Yes, hello, you hear me?
Yes, we can, Julia.
Okay, well, I don't know. For the camera. Okay, yeah, I think I even can put the camera. No, I just wanted to thank both of the speakers for their really nice talks, and also the ISTA are kind of like partner in crime in terms of seed science and technology for organizing these meetings, because they're really very interesting, and a lot of our students are looking at it as well. And I think it's really how we should collaborate together to teach people about seed science and make younger people interested. So really a big thank you to all of you, and let's continue this way. Thank you very much.
Thank you, Julia. And I think it's, as we have no further questions, time to say goodbye. And again, you find it on the ISTA YouTube channel. And if you need to look at it again, thank you to both of you. Karen, it's still early morning, so
Sorry, Andres, I just wanted to say I think that question about the seed coat ratio, it might have been a confusion because it's 2 a.m. in the morning and I said the wrong
yeah.
thing. The seed coat ratio is the ratio of the seed coat to the whole seed, not the embryo to the whole seed. So apologies for that. And maybe you could just go back and delete that in the recording.
If people have to look at until the end, probably.
The correction is recorded now.
Oh, thanks.
Okay. Thank you very much. It's still time for you to catch up with some sleep, I would say, in Australia. And thank you also, Elisa, for joining here. It was a more moderate time for you.
Yeah.
Um, thank you for both of you, and thank you, Julia, for your nice words as well. Take care and goodbye. Bye bye.
Thank you.
Bye all.
Bye.